How can a single op-amp perform complex functions? Imagine a tiny electronic device that can do many different jobs all on its own. That's what a single operational amplifier, or op-amp, can do when set up correctly. It might seem simple at first, but with the right external parts, it can handle some pretty complicated tasks. Think of it like a versatile tool that can switch roles from a calculator to a filter or even a signal processor. An op-amp is basically a very high-gain differential amplifier. It takes two input signals and amplifies the difference between them. It also has high input impedance, meaning it doesn't draw much current from the source, and low output impedance, so it can drive other circuits easily. Usually, we connect resistors and capacitors around the op-amp to control what it does. These external components are the secret to turning a simple amplifier into a signal manipulator. One way a single op-amp performs complex functions is through feedback. By connecting resistors and capacitors in the feedback loop, we can make it do calculus operations. For example, if we replace the feedback resistor with a capacitor, the circuit becomes an integrator. This means it outputs a voltage proportional to the integral of the input voltage over time. It's like the circuit is doing math in real time. Similarly, if we put a capacitor in series with the input resistor, it becomes a differentiator, producing an output proportional to the rate of change of the input signal. These configurations turn the op-amp into an analog computer, capable of solving differential equations instantly. Another trick is creating filters. By combining resistors and capacitors, a single op-amp can make active filters that let certain frequencies pass while blocking others. For example, a low-pass filter allows low frequencies to go through, while high frequencies are reduced. A high-pass filter does the opposite. Bandpass filters let a specific range of frequencies pass, which is useful in audio processing and communication systems. These filters are essential for cleaning up signals or isolating certain signals from noise. The gain of the op-amp circuit can also be precisely controlled by resistor ratios. By adjusting these resistors, you can set the exact amplification needed. Sometimes, you need to add offset voltages to shift the output up or down, which is useful in sensor applications. This way, the same op-amp can perform linear functions like multiplying and adding signals, which are fundamental in many analog systems. Modern op-amps designed for single supply operation can work with just one power source, like a battery. They use a reference voltage called virtual ground, which is usually at the middle of the power supply voltage. This allows the op-amp to handle AC signals centered around this virtual ground, making it perfect for portable and embedded systems where space and power are limited. Designing these circuits involves writing equations based on Kirchhoff's laws and the ideal op-amp assumptions. These assumptions include infinite gain, zero input current, and that the voltage difference between the input terminals is nearly zero when negative feedback is used. By solving these equations, engineers can choose the right resistor and capacitor values to get the desired behavior. In real-world applications, an op-amp configured as an integrator can be used in waveform generators or control systems. Active filters built with a single op-amp are common in audio equipment and sensor signal conditioning. They can perform multiple functions in a compact package, saving space and cost. So, the reason a single op-amp can handle complex tasks is because of its high gain and the clever use of external passive components. These components shape the input-output relationship, turning a simple amplifier into a multi-talented signal processing tool. Whether it's doing calculus, filtering signals, or controlling gain, a single op-amp can do a lot more than meets the eye.